Okay, so my name is Håkon, and I'm currently doing a PhD at the Department of Computer Science. And what I'm going to talk about today is what I call deep privacy, which is what I worked in my master thesis, which is looking at how you can take a face in an image and then try to replace this face with something that looks realistic, but in this way I'm able to anonymize my identity. Most of you probably don't know who I am. 2 years ago I was sitting at a brain event myself, looking at the presentations, and I'm very happy to be here today. I graduated from computer science here at NTNU last year, where I wrote about anonymization in images. And during my master's, I was both doing an exchange year at UC San Diego, where I specialized in computer vision and deep learning. And I've also been working at Itera and Cisco, where I've been mostly working with machine learning methods. Then I decided to do a PhD here at NTNU, and if anybody has questions about how that is, please answer me after, or ask me after the talk. And one more thing, I'm part of the NTNU Autonomous Perception Group, which is working on computer vision systems for autonomous vehicles. And that's me right there. And my project started with that we wanted to record images in Trondheim. We have this vehicle that we want to record a bunch of images to do research on. And if I start driving around in Trondheim and then recording a bunch of people with their faces, I'm going to have a lot of privacy-sensitive information. So my task in this project was, how can I anonymize the persons? One thing that we want to do with this is that, for example, if we're walking on the street in London, so this is a YouTube video, you're recording a bunch of people. And we want to use this data for computer vision research. So one way to anonymize this data is doing kind of what Google is doing on the street maps, where they just blur out all the faces. But that's very easy for a human to see that, of course, this is corrupted. This face is no longer a face, it's a blurred face. So instead, we want to replace all the faces and to make it still look somewhat realistic. Something you might notice here is that the faces are flickering a lot, and that's mostly because my method is an image-based method. So I'm not looking at video sequences, I'm just looking at a single image at a time. So I'm going to go a bit more technical than the other presentations today. And the system I developed is kind of a two-stage system. So I have this first part that is responsible for detection of the faces. This is really not what I decided to work on, because face detection is almost a solved problem, or the methods that we have today is very good at it. But the second stage of my model is what I call a generative model. And the generative model is responsible to take a face that is already detected, and I first just clip out or remove all the information that might show the identity of the person. You might also see that I'm including a pose of the face, which is just saying where in the image is the different landmarks of the face. So where in the image are the eyes, or the nose, or the ears. Then I'm putting this through, I'll call it a generator now. So it's just taking this input information, this conditional information, and then generating something that hopefully looks realistic. So this, of course, looks like a face, this fake image that I generated, and that's what I want my generator to do. For those who have done some kind of machine learning, this is just a convolutional neural network. But you can look at it as a black box model for this presentation. So if I just assign this network and run this conditional information through it without training it, the original image is going to, or the generated image is just going to look like some corrupted garbage. So this is kind of the thing I want to talk about today, is how can you generate or make this generator learn what is a face. given this conditional information, how can I generate something that looks realistic, that looks like a face to a human? So for those who have done any kind of machine learning, you know that when you have a neural network, you always want some way to optimize your network or train your network. So you want to define how do you judge your model? And this is something we usually call a objective function. It's something you want to train based on to make the network learn what a face is. So if I have my generator that is not trained at all, I want to give it some kind of feedback on how good it is at generating a face. So we want this objective function to say, does the generated image look like a face? So if you look at this fake generated image, it's obviously not a face for us. But expressing this in mathematical terms is not that easy. Also, I want this generated face to correspond or look similar to the conditional information, the input image or the original image I had. So one way to define this objective function is that I can just look at a patch of the image. So I have my generated image and my real image and look at the difference. So I can just take a single pixel and then I can measure some kind of L2 loss or L1 loss. It's just taking a pixel in the original image and the generated image and measuring the distance. So if the distance is 0, you generated exactly the same image. But this is really not a good objective function, and I'm going to show you now. Why now? So I have my one image right here, and I'm going to translate this in 2 ways. So I'm going to make a blurred version of this image, and then I'm going to take the original image again, and I'm just going to shift it. So you can barely notice the difference right there, but there's a 2-pixel shift. Now, if I look back at the objective function that I just created, this L2 distance between the pixels, and I measure which image is most similar. For example, if I look at these 2 images I want to say which image is most similar to the original one, I'm definitely going to select the shifted one. There's no doubt for a human. But this L2 distance is always going to select the blurred one. So this is really not a good measure to say how good an image looks. So this objective function of L2 distance does really not work. So I'm going back to my generator. I have my generator that created some kind of fake image, and I have my real image. One way I can optimize this is that I can look at this generated image and say that, well, this is not a real face because this part looks corrupted. And then I can say that to my generator, and you can optimize it some way. And then you do this again and again and again, and after some time it's going to learn what a generated image is, or what a real face is. Of course, doing this in practical is impossible. I can't evaluate every image this generator makes. So you change it with something called a discriminator. And this is something known as generative adversarial networks for those who are familiar with it. The way it works is that you take this conditional information, you feed it through the generator that generates some kind of fake image. It might look like a face, it might be completely corrupted, and then this discriminator gives some kind of feedback to say that this image looks real or this image looks fake. And of course, this discriminator has the conditional information right here, so it knows something about how it should look like. This is, of course, going very quick and a very abstracted explanation of what a generative adversarial network is. But if you start to define this objective function right here, and you start to train your network, when you initialize it, it might look something like this. And then you train it over time, and it's going to look more and more like a face. So for those interested, this takes about 20 days to train on 2 GPUs who cost 100,000 Norwegian kroner each. So it's pretty expensive to do this. And that's one of the difficulties of my research. So now I know how to generate a face. I can do face detection. And if you just put all of this together, you have this original image, and I'm able to anonymize this. And this is the resulting image. Again, in a bit more realistic scenario, you have probably a typical scenario for an autonomous vehicle, a bunch of people crossing the street, and this is the anonymized image. And I'm also going to show you a video to show it a bit more close detailed.
You still got a job.
Oh.
John, you worry about getting wet? I do. But my worry is...
So probably the sound isn't good.
We're underestimating these guys. And my worry is that a lot of people have been pranked saying that they're going to die. My worry is that you're going to get 10 scripts and that you're going to have dynamite stuff. There's going to be scenes with people you've never had scenes with before, amazing narrative arc. You're going to emerge the hero of the piece. The day after, please find script amendments for episodes 1 to 10. Changes made, you're not in a single frame of it. All the best.
Is that possible? Could that happen? They could do that.
They can make whatever they want. Whatever they want.
Okay, Sophie, Sansa's been through a lot. Just so much. Before the season...
It's not real, folks.
Yeah.
Annie, no!
Oh, sorry.
It is real.
Right, so that's just to give you an idea how this system works currently. It's not perfect, but it's definitely a start to do automatic anonymization. This method has a lot of limitations currently. First of all, is face anonymization enough? So most of you recognize who these two people are. If you didn't see it, it's Trump and Obama. And you know, there's definitely other parts of the body that is able to identify you. Some of the faces are really not looking too realistic, and this is why I'm doing a PhD on it. It's not a master project that is possible to solve in 1 year. Yeah. So all of my code is open sourced. You can search up deep privacy on Google, and you should be able to test it out. Next week, I'm releasing a Python library, so you should be able to kind of anonymize an image with 4 lines of Python. So just building the anonymizer, reading the image, and then anonymizing the image. Also, I set up a web server today, so you can test out the system yourself and see how it works. So that's privacy.hukkelås.no. And that's pretty much what I had today. I'm going to show you a short demo before ending this. Okay. So I can take any questions if you have it while this is starting. Yeah.
So thank you for a very interesting talk. I was wondering, have you considered like adversarial attacks against your system, in the sense that can I train some network to produce a face mask that when I walk on the street wearing this mask and rob a bank, the Tesla on the street will show you robbing the bank?
Well, that's an interesting question. So, I mean, this, yes, definitely. It's, well, so the question is, so first part of the question is that my system is able to generate all kind of faces. Well, it's not currently, but let's assume that it's able to generate my face on your face. And the second part is that if there exists an adversarial attack. I haven't seen that much adversarial attack on kind of these kind of networks yet, but I'm not sure where the use case would be, because you would. Yeah, but well, I would assume that you had some kind of security cameras that's not anonymizing it. But if you can design some kind of adversarial attack to generate the correct face. I haven't seen work on it, but maybe. Yeah. Yeah.
How do you ensure that the face that is generated is not the actual face of the person? I mean, if your generator is good enough, it could probably get closer and closer to generating the actual face.
So in my work so far, I haven't looked at this specifically, but there's work at the Technical University in München that has looked into, first of all, you generate some kind of ID for the person that the original image had, and then you make sure that the generated face is not similar to this ID. So you're using some kind of face recognition software to generate this descriptor of the face, and then you make sure that the descriptors are completely different. Yeah.
Well, about the face mask robbing, just if there's some random element in the way you generate it, because as soon as there's something random, they wouldn't just recognize it and then just start, making the same one. As soon as there's some random element, you would never be able to reliably rob banks with masks and just gamble on it making the correct face. So I mean, that's not the hardest one to solve, at least.
Yeah. So can I take 2 minutes to show the demonstration?
So you want the last question?
Oh yeah, sure. Yeah.
Yeah, you just.
Yeah, let's take the question.
It's related. So in the video, there was some continuity, even though you said that you did a picture at the time. So it's picking up some kind of context from the kind of the rest of the head.
Yeah. So the way I created the video is that I set the same. So I have a vector that says how the face is going to look, which is just a bunch of random numbers, 500 random numbers, that is going to say something about how the face is going to look.
Okay, so that was
So in the video, I had the same vector all the time, so it was constant.
Yeah.
But I'm going to show you here that it's possible to generate different faces for the same original one.
And second question, how big is this model then when you have trained it?
So this is about 12 million parameters, which is about 20 convolutional layers. So it's not that big. Yeah. Okay. So this is a demonstration that I made. And one thing I can, so I have this vector that says something about how the face looks. So I'm running this on my Mac, so it's probably going to be a bit slow. But I can generate different faces for the same original information. And what the actual model sees is just some cutout of the face. And this, you can see the face annotation, right? So if I'm toggling this, I'm not sure if you can see it on the screen right here, but there's small dots right here that says that we're using the different landmarks of the face. And I can also take these landmarks and just slightly move them. And you can see I moved my nose about here now. So you can do different transformations of the original face. Yes. To wrap up, if you're interested in learning more, we have 2 publications on this area. You can just search up my name on Google Scholar and you should be able to find it. Also, we have an article on NRK, and if you're really interested in this stuff, you can take my course or the course I'm involved in, which is computer vision and deep learning. Yeah, thank you.
Thank you so much, Håkon. Do we have any other questions following up?
Have you considered an application using this, for example, to, I don't know, on the fly replace advertisement in a movie or something, like, oh, this company hasn't paid for this advertising here, so you're going to swap it out? Or
Never consider it. It's probably possible though with this, yeah. I'm not sure if the thing with advertisement, you would have, what you want to generate, what you want to place in. So you have a 3D structure usually of a movie, so you could do some magic to place it in then.
Some more?